Welcome everyone. Today, we'll explore best practices for pipeline integrity, covering prevention, detection, and mitigation. Our goal is to ensure safe and reliable pipeline operations through proven strategies. Pipeline integrity is critical for transporting essential resources safely. We'll start with an overview of its importance and why it's a strategic necessity. Pipeline integrity refers to the ability of a pipeline system to operate safely and reliably throughout its lifecycle. It is a critical aspect of energy infrastructure because pipelines transport essential resources such as oil, gas, and water over long distances. Maintaining integrity ensures environmental protection, public safety, and operational efficiency. Failures can lead to catastrophic consequences, including spills, explosions, and financial losses. Therefore, integrity management programs are implemented to monitor, assess, and maintain pipeline health. These programs involve a combination of engineering practices, regulatory compliance, and advanced technologies. The concept encompasses prevention of damage, early detection of anomalies, and effective mitigation strategies. By prioritizing pipeline integrity, operators can reduce risks, comply with international standards, and build trust with stakeholders. This introduction sets the stage for understanding why pipeline integrity is not just a technical requirement but a strategic necessity for sustainable operations. Next, let's look at common threats and failure modes that compromise pipeline integrity. Pipelines face numerous threats that can compromise their integrity. Corrosion is one of the most prevalent issues, occurring internally due to transported fluids or externally from soil and environmental conditions. Mechanical damage, such as dents and gouges, often results from third-party interference like excavation activities. Material defects, including welding flaws and manufacturing imperfections, can lead to structural weaknesses. Operational factors such as pressure fluctuations and temperature extremes also contribute to stress on pipeline components. Additionally, natural hazards like earthquakes, floods, and landslides pose significant risks. Understanding these threats is essential for designing effective prevention and detection strategies. Operators must conduct regular risk assessments to identify vulnerabilities and prioritize maintenance activities. By categorizing threats into internal, external, and operational factors, companies can develop targeted integrity management plans that address each risk comprehensively. Pipeline integrity is governed by strict global standards. Compliance is not optional, it's essential for safety and reliability. Pipeline integrity management is governed by stringent regulations and standards to ensure safety and reliability. Key organizations such as the American Petroleum Institute, API, the American Society of Mechanical Engineers or ASME, and the International Organization for Standardization or ISO provide comprehensive guidelines. API 1160 focuses on managing system integrity for hazardous liquid pipelines, while ASME B31.8 addresses gas transmission and distribution systems. ISO standards offer frameworks for risk assessment and quality management. Compliance with these standards is not optional, it is a legal and operational requirement. Regulatory bodies mandate periodic inspections, documentation, and reporting to verify adherence. Failure to comply can result in severe penalties, operational shutdowns, and reputational damage. Operators must integrate these standards into their integrity management programs, ensuring that design, construction, operation, and maintenance activities align with global best practices. This approach fosters a culture of safety and continuous improvement across the industry. The prevention starts with design and material selection, followed by a robust maintenance cycle. Preventing pipeline failures begins with robust design and material selection. Engineers must consider factors such as operating pressure, temperature, and environmental conditions when choosing materials. High-strength steel with appropriate coatings is commonly used to resist corrosion and mechanical stress. Protective coatings and cathodic protection systems are essential for mitigating external corrosion. Design should incorporate features that minimize stress concentrations and allow for thermal expansion. Additionally, implementing redundant safety systems and pressure relief mechanisms enhances reliability. Preventive strategies also include route selection to avoid geohazards and areas prone to third-party interference. By integrating these considerations during the design phase, operators can significantly reduce the likelihood of integrity issues throughout the pipeline's lifecycle. Prevention is always more cost-effective than repair, making proactive design a cornerstone of pipeline integrity management. Preventive maintenance cycle number 1 is regular inspections, including activities as visual and instrument-based checks with frequency quarterly. Preventive maintenance cycle number 2 is cleaning, including activities as pigging to remove deposits with frequency semi-annual. Preventive maintenance cycle number 3 is coating repairs, including activities as touch-up damaged areas with frequency as needed. Preventive maintenance cycle number 4 is cathodic protection checks, including activities as system performance verification with frequency annual, and preventive maintenance cycle number 5 is documentation form the backbone of preventive maintenance, including activities as update maintenance records with frequency continuous. Early detection is vital. Let's review the technologies used for inspection. Early detection of anomalies is vital for preventing pipeline failures. Inline inspection, IL, tools, commonly known as smart pigs, are widely used to assess internal conditions. These devices employ technologies such as magnetic flux leakage or MFL and ultrasonic testing or UT to detect corrosion, cracks, and wall thickness variations. Supervisory control and data acquisition, SCADA, systems provide real-time monitoring of pressure, flow, and temperature, enabling operators to identify irregularities promptly. Acoustic sensors and fiber optic cables are also deployed for leak detection, offering high sensitivity and rapid response. Remote sensing techniques, including drones and satellite imagery. Enhanced surveillance of inaccessible areas. Combining these methods creates a layered detection strategy that improves reliability and minimizes downtime. Investing in advanced detection technologies ensures that operators can act swiftly to mitigate risks before they escalate into major incidents. When anomalies are detected, mitigation strategies restore integrity and minimize impact. Mitigation involves implementing corrective actions to restore pipeline integrity after detecting anomalies. Common repair methods include composite wraps, welding sleeves, and clamp installations, which provide structural reinforcement without requiring full pipeline replacement. Pressure reduction is often employed as an immediate measure to minimize stress on compromised sections. In severe cases, pipeline shutdown and segment replacement may be necessary. Emergency response plans are critical for managing incidents effectively. These plans outline procedures for isolation, containment, and communication with stakeholders. Training personnel and conducting regular drills ensure readiness for unexpected events. Mitigation strategies must also address environmental restoration and regulatory reporting to maintain compliance. By combining technical repairs with robust emergency protocols, operators can limit the impact of integrity breaches and safeguard public safety. Real-world examples and innovations show how technology is shaping pipeline integrity. Case studies provide valuable insights into the effectiveness of integrity management practices. For example, a major pipeline operator successfully prevented a catastrophic failure by implementing predictive analytics and real-time monitoring, reducing downtime by 30%. Another case involved the use of drones for aerial inspections, which improved coverage and reduced costs. Future trends in pipeline integrity include the adoption of digital twins, which create virtual models of physical assets for continuous monitoring and simulation. Artificial intelligence and machine learning are being integrated into SCADA systems to enhance anomaly detection and predictive maintenance. These innovations promise to revolutionize pipeline integrity management by enabling proactive decision-making and reducing human error. Embracing these technologies will position operators at the forefront of safety and efficiency in an increasingly complex energy landscape. Let's summarize and key takeaways: the best practices for pipeline integrity. Pipeline integrity is a multifaceted discipline that requires a proactive approach to prevention, detection, and mitigation. Best practices include designing pipelines with robust materials, implementing protective coatings, and conducting regular maintenance. Advanced detection technologies such as smart pigs, SCADA systems, and remote sensing play a crucial role in identifying anomalies early. Mitigation strategies, including repairs and emergency response plans, ensure rapid recovery from incidents. Compliance with global standards reinforces safety and reliability, while emerging technologies like digital twins and AI offer promising advancements. By integrating these practices into a comprehensive integrity management program, operators can safeguard assets, protect the environment, and maintain public trust. The ultimate goal is to achieve zero incidents through continuous improvement and innovation.